Thermal insulation. That is one of the first things that comes up when you're talking about reducing the energy demand. But how does thermal insulation work and how effective is it? That is the topic of this lecture. Because of the temperature difference between indoor and outdoor, heat starts to flow through the building envelope, the heat transmission. Each part of the building envelope contributes to the heat transmission, depending on the size and thermal properties of the several building elements in the envelope. The thermal transmittance, also called the U value, is the most important thermal property of a building element. The transmission heat loss through a part of the building envelope can be calculated with this formula. The heat flux through the building envelope in watts per square meter equals the U value of the building part times the temperature difference between indoor and outdoor. The U value is the thermal transmittance of the building element, with the unit watt per square meter per Kelvin. This is a very important property of building components. It says how big the transmission loss per square meter is per degree temperature difference between indoor and outdoor. So the lower the U value, the better. Let's have a look at some examples of U values for uninsulated building elements. An uninsulated masonry wall has a U value of 2.7. A wall with an uninsulated air cavity 1.7 and a plywood roof 3.5. How can we reduce the U value of these uninsulated building elements? For that, we have to look somewhat deeper into the U value of multi-layered building elements. The U value is 1 divided by the total thermal resistance of the construction. Or, vice versa, the total thermal resistance of a building element is 1 divided by the U value. The total thermal resistance of a wall is composed of the resistance of the individual layers with an extra resistance on the inner and outer surface we call the surface resistance. These surface resistances are determined by heat convection and radiation at the surfaces. We won't go into detail about the surface resistances. For now, it's enough to know that together they contribute around 0.17 to the total thermal resistance. What we need to know now is how the thermal resistance R of a layer of a material can be calculated. This is how to determine the thermal resistance of a layer of any solid material. The resistance R equals the thickness of the material divided by a material property called the thermal conductivity. These are some examples of thermal conductivities. There are, generally speaking, 4 groups of materials. Metals with a very high thermal conductivity, higher than 50, like steel. Stony materials with a high thermal conductivity, around 1.5. Concrete, for example, has a thermal conductivity of 2. Wood and plastics with a relatively low thermal conductivity. Wood, for example, has a thermal conductivity of 0.15. And insulating materials like mineral wool with a very low thermal conductivity, less than 0.05. In the course reader and on the internet you can find the thermal conductivity for all kinds of building materials. Let us look at an uninsulated wall and see what happens if we add a layer of thermal insulation material. As we have seen before, the U value of the uninsulated 20 cm thick masonry wall is 2.7. So the total thermal resistance is 1 divided by 2.7 is 0.37. A 50 mm layer of mineral wool insulation has a thermal resistance of 1.39. So in this case, the total thermal resistance is 1.76. This results in a U value for the insulated wall of 0.57. So, adding 50 mm of insulation material reduces the heat transmission losses by almost a factor of 5. You can do this calculation for different insulation thicknesses, and then you get this graph. What you can learn from this graph is that the first centimeters of insulation are the most effective. Adding more insulation, if you have already 20 centimeters or more, has very little effect. You can't just put a layer of insulation material against your wall. It has to be applied in a proper way, on the inside or on the outside of the wall, or sometimes in an existing cavity. It has to be detailed in such a way that moisture problems caused by internal condensation will be avoided. If you're not familiar with this, you should always consult a building engineer before you start insulating your building. Here we'll show you how the thermal insulation is applied in the Pret a Loger house. On the north facade, insulation is applied to the outside of the existing wall. The original outer masonry slab is removed and the 200 mm thick insulation layer is applied, covered with thin brick tiles. On the south side, the cavity in the existing brick wall is injected with loose fill insulation material. This performs less than the exterior insulation on the north side, but the greenhouse on this side also helps to reduce the transmission losses. So far, we have talked about the thermal insulation of walls, and you can apply the same approach to roofs and floors. But how about windows? For glass, the thermal transmittance is called the UG value. Single glass has a UG of around 5.7. The glass itself has almost no thermal resistance. The surface resistances mainly contribute to the total thermal resistance. So this U value is around the highest any building element can have. To reduce the U value of glass, a few technologies are applied. First, adding additional layers of glass, thus creating one or more air cavities. By adding one extra layer, double glazing is created with a U value of 3, which almost halves the heat losses compared to single glass. Double glazing is common nowadays. Triple glazing is more and more applied, and even quadruple glazing is on its way. The second technology is to apply a so-called low E coating, which reflects the infrared radiation and reduces the heat transmission through the cavity. This coating is a very thin, invisible layer of just a few molecules of metal. By adding this coating, the U value of double glazing can be reduced from 3 to 1.8. Glass with this type of coating is called HR++ glass. And the final technology is to replace the air in the cavity with another gas that has a lower thermal conductivity, like argon or krypton. Starting with double glazing, with a low E coating and an air-filled cavity, the U value is 1.8. It reduces to 1.5 with an argon-filled cavity and to 1.1 with a krypton-filled cavity. With these technologies, modern insulating glass can have a U value as low as 1 or even 0.5, which is very low compared to single glass. But compared to a well-insulated wall with a U value of 0.2, it is still relatively high. This means that reducing the size of the windows is also an important measure to reduce the transmission losses. To summarize, you learned what the thermal transmittance of a building element is and how it is determined by the thermal resistance of the layers, which is determined by the thermal conductivity of the building materials. And you learned how the thermal transmittance of glass can be reduced.